Financial Modeling, Topic 17, Black-Scholes-Merton, or BSM, Option Greeks, and Delta Hedging, copyright Lou Gaddis. References include Financial Modeling, 4th edition by Simon Benenka, chapters on options, Black-Scholes model, the Greeks, Monte Carlo methods, simulating stock prices, simulating options and option strategies, and using Monte Carlo methods for option pricing. Section 1. Compute and understand the BSM, Black-Scholes-Merton, or sometimes Black-Scholes Greeks. So from previous topics, we've gone over the Black-Scholes call and put formulas and functions. So here is a function for calculate the value of a call, BS call, the function to calculate the value of a put, BS put, a function to calculate the implied volatility of a put, and the implied volatility of a call. Now when we talk about the Greeks, what we're really talking about is derivatives of either the BS call formula or the BS put formula with respect to the stock price, the volatility, the interest rates, the maturity. So we're looking at derivatives of those functions, call and put, with respect to those underlying variables. So the Greeks are partial derivatives of the call and put formulas, and they show you what happens to the value of an option using the model when one parameter changes. We have delta, gamma, vega, theta, and rho as the Greeks. Delta is the first derivative of call or put value or function with respect to underlying changes in the spot price of the underlying asset. And that number, that delta, will tell you the change in option value when the stock price increases by $1. Gamma is the only second derivative. That tells me how the delta changes as stock prices change. So it's the second derivative of the call or put value function with respect to underlying changes. Vega is the change in the option or put price with respect to changes in volatility. So it tells you specifically if implied volatility goes up or down by 100 basis points, it tells you what the change in the value is. Theta, or sometimes called time decay, is the change in the value of the call or put with respect to time. So theta will tell you the change in value as the option gets 1 day older or 1 day closer to maturity. And finally, rho. What is the change in value of the call or put if the interest rate, the risk-free rate of the same maturity as the option goes up or down by 100 basis points. These are the Greeks. I have some interim functions to calculate D1, D2, ND1, ND2, and then you start seeing the functions here. Here's one for BS call delta, BS put delta, BS call gamma, BS put gamma, BS call vega, BS put vega, BS call rho, BS put rho, BS call theta, and BS put theta. So you can copy all of these functions into a VBA-enabled workbook or macro-enabled workbook, and we're going to insert them and calculate the Greeks for this 6/15 March call and put on Goog. So we'll go to our spreadsheet. The functions are already in there, so if I go to my Developer tab, Visual Basic, you can see in Module 1, I have BS call, BS put, and put call and put vol, and then I have all the Greeks. So I'm going to insert BS call delta first, equals BS call delta. I'm going to hit open, and then I'll click on the insert function, and I'll put in my underlying stock price, and I'm going to anchor everything, hit F4. I'm going to put in the strike price, 615, anchor that. The volatility, 18.67 is the implied volatility. The interest rate, 10 basis points, anchor that. Maturity, 0.05 years. And the dividend yield of 0. So I'm getting a delta of 49.78 cents. And what that tells me specifically is if the underlying stock price of the call goes from, say, 614 to 615, a $1 increase, it's telling me the call should increase by about 50 cents. So the price should go from about 10.05 to 10.55. And I can check that out. Let's change that from 614 to 615 and see if this number right here changes to 10.55. And it does. So I'm going to undo that. I'll then calculate the BS put delta I just copied that since everything's anchored. I'm going to just change the word BS call delta to BS put delta. And that's negative 50 cents. So if I was looking at a put, if the stock price went up from 614 to 615, the put price would fall by 50 cents. Now I'm going to copy these functions down. I'm going to change the word BS call delta to BS call gamma. Change that to Vega. I can only do this because I know the parameters in the same order. Theta. And rho. I'll then copy that across. And so now I have this. So I'm going to highlight this and change call gamma to put gamma. Change that to put. And the last two. So these are my Greeks. So again, delta told me as the stock price increases, the call increases by 50 cents, the put decreases by 50 cents at the current level of these parameters. Gamma tells me the change in delta, and notice it's the same for both options. So it's actually, you can think of this as a 0.015. So what would happen is if the stock price goes up by $1, I'd expect the delta, since gamma tells me how delta changes, I'd expect the delta to increase by about 0.01. So I expect this to go up to about 50 cents or 51 cents. So I can try that out. If I change this to 615, what I'll see is if this goes up by about 1.50 cents. And it does. I'll hit undo. Vega tells me if implied volatility goes to 19.67, the option price should increase by 55 cents. This should go to about 10.60 right here. And it does. Theta tells me if this option had only 12 days to maturity, the option will lose 40 cents. So we'll see if this drops. And it does. I'll hit undo. And lastly, rho, this tells me if interest rates increase by 100 basis points, so I'm going to make this interest rate 1.1%, and you'll notice this went up by about 15 cents. I'll undo that. So those are the Greeks. Notice that BS call delta and BS put delta are different and have different signs. The call delta is always positive. There's an increasing function of call price with respect to stock price, and it's negative for put. The gammas are the same. The Vegas are the same. And then theta and rho are different. So those are the Greeks. It tells you the change in the value of the call or put with respect to underlying changes in variables. And graphically, sometimes we'll like to look at what the delta and gamma actually mean. If I look at, say, the call or put price on the y-axis and underlying stock price on the x-axis, and we're looking at a call in this situation and a put over here, a call has a positive delta, and what you'd see is the actual price yield, the actual relationship between the call value and the stock price is a convex function that's increasing. The slope at the current call price and stock price is the delta, and the curvature is measured by the gamma. For a put, that's a negative relationship with positive convexity or positive gamma. And what you see is the negative slope, and that's why you get that delta. Positive slope, that's why you get that delta. And both of them have positive convexity. In other words, both of those functions are facing upwards, or bending upwards away from, or upwards, So that is the BSM Greeks. In the next topic, we'll use those Greeks to perform return attribution.